Good morning, everyone, and welcome to the webinar. My name is Caroline Stewart, and I work in the marketing team at Crate.io. I'll be your moderator for the webinar this morning. I'm joined this morning by Tanay Pant, who is your presenter on the webinar today, and he'll be presenting the curious case of time series data. But before I hand over to Tanay, I'm going to go through a few housekeeping items. If you have problems with the sound or you can't see the screen share, then please let us know through the chat. We'll take Q&A at the end of the presentation, but if you do have a question that you think of throughout the slides, then please pop those in the questions box that you see on the screen, and like I say, we'll take those at the end. And then finally, we will be recording this session and we'll be sending you out a link to that within the next few days. So without further ado, I'll hand over to Tanay. Thank you.
Thanks, Caroline. And hello, everyone. Welcome to today's webinar on the curious case of time series data. I'm really excited to be amongst all of you here. So today we will talk about a couple of topics, which include time series data, what it is, and how its workload differs from other forms of data. We will also talk about different use cases where time series data is being used quite widely these days. We will take a look at how CrateDB helps in dealing with machine data and what are the technical aspects of the database that make it so efficient to handle the workload of Industry 4.0. And then we will see CrateDB running on Azure, the different things that you can do with it, and how you can spin up your own cluster on Azure. And finally, we will go through a case study of a smart factory which made six-figure savings in 2018 by making a switch to CrateDB. And we will also do some querying on their machine data. My name is Tanay Pant, and I currently work as a developer advocate at Crate.io in Berlin. I really enjoy working with time series and sensor data. I'm a tech speaker for Mozilla and volunteer to their various projects in my spare time. I have published books on Firefox OS, building a virtual assistant on Raspberry Pi, and web-based virtual reality. I'm also an Intel software innovator in the field of IoT. And towards the end of this webinar, I will share my email and Twitter handle. So if you have any questions after the event or have any interesting project ideas, please feel free to get in touch with me. I'd be really happy to collaborate. So let's get started. Before diving into the use cases of time series data, let's talk a bit about time series data itself. What is time series data? And most importantly, how does it differ from other different forms of data? So to answer this question, imagine a sensor. This sensor is sending streams of data over a period of time. If you were to plot this data, one of the axes would be time. And as compared to some other workloads, the data is not added as an update to the database. So if you think of a platform like WhatsApp, each time you set a new status, it rewrites your previous one, as this change is made as an update to the database. Time series data is added as an insert, and this is the primary way of adding it to a time series database. Time series databases introduce efficiencies by treating time as a first-class citizen. So having such a rich amount of historical data allows you to delve into all the aspects of your operation, such as analyzing the past, monitoring the present, and predicting the future. Now that all of us have an idea of what time series data is and what it tends to look like, let's play a game that I like to call time series or not. So is the data that is denoted by this graph time series or not? So what we are going to do is we are going to launch up a poll. So I'm going to give you 2 seconds to quickly look at the graph to determine if it's time series or not. And Carolyn, could you please put up the poll so you can enter your answers if you feel that this is time series, yes or no. Gonna wait for a few seconds here. And I think we can shut down the poll now. Cool. So as all of you said, yes, this is an example of time series data, as we are measuring metrics such as temperature and pressure against time. So time series or not, let's have a few seconds to take a look at the graph, determine if this kind of graph denotes time series data. And Carolyn, let's put on the poll. All right, same question, time series, yes or no? Okay, I think we can take this off now. So all of you are correct. No, this is not an example of time series data, as we are measuring the production of good and bad bottles against the different production lines. Last one, time series or not. So let's take a quick look at this graph. And Carolyn, please cue in the poll. Question of the century, time series, yes or not? Okay, I think we can close the poll now. And let's take a look at the results. Most of you are correct this time. So here again, we have an example of time series data as we are measuring the downtime hours of the New York and Florida factories against months, which is essentially time. Now, if you take a look at the abstract use cases of time series and the kind of data generated, you can categorize them roughly into two types. So first of all, we have IT and system monitoring. So this can be termed as the traditional use case of time series databases. So this can be characterized through tens of hundreds of metrics or sensors, real-time write functionality, reality of complex queries, and data volumes that usually fall in gigabytes. So if you think about the different databases in this segment, InfluxDB is an excellent example as a database for this category. And then we have industrial sensor data. And this is an emerging sector that I feel has not been talked about enough. So this is characterized through hundreds of thousands of metrics or sensors and real-time queries that are under highly concurrent load and must access gigabytes to hundreds of terabytes of data. And CrateDB is an especially good fit for this category. And then there are some other characteristics that separate the two use cases, like the projects that fall under the first category tend to be internal IT services, and the data in the database or monitoring are often not mission critical. However, the projects that fall in the latter category are often mission critical, transformative, and enable real-time data-driven decision systems. And if we look at the last decade, in the last few years, it's a machine data world. And machine data means explosive growth. So in 2018 itself, we saw a boom in the number of IoT devices and their use cases. So there was an increase in the use of IoT and sensors in different contexts, such as smart factories, which we also refer to as Industry 4.0, and smart cities. The total number of IoT devices is moving towards 20 billion by the year 2020. And every second, another 127 devices are being connected to the internet. Just for an example, take a Boeing 787, which generates half a terabyte of data during a single flight. And if we talk about the plastic manufacturing industry, there's a wide array of data being produced per bottle. And then there's data per production line, with about as much as 10 production lines per plant. And this data is being generated by around 950 sensor types. And that's just one factory. And this particular company has 180 factories in 45 different countries. That means data on billions of bottles. And there's a good chance that the bottles that you have in your refrigerator have been sending their data to the Crate data platform during its production cycle. But we will talk more about this company and the data generated by it in just a short while. So at Crate.io, we have been working on developing technical architecture in IoT and time series field over the past 5 years. We have a co-selling agreement with Microsoft, and our client portfolio includes companies like McAfee, Nokia, Rauch, ALPLA, and many more. So earlier this year, Crate.io was also named a Cool Vendor in the Gartner 2019 Cool Vendors in Manufacturing Operations report. So to learn about the CrateDB ecosystem, let's start off by going into the heart of the honeycomb to the core technology and talk about CrateDB and what makes it stand apart from the various other databases in this segment. So CreateDB is a new kind of distributed SQL database that is best suited for handling industrial time series data due to its ease of use and ability to work with many terabytes of time series data with thousands of sensor data structures. CreateDB is quite simple to install. You can spawn an instance of CreateDB with a single line on your terminal or on Docker. CreateDB uniquely combines standard SQL with NoSQL benefits. It operates on a shared nothing architecture, and the various nodes in a cluster coordinate seamlessly with each other. And the execution of write and query operations are automatically distributed throughout the nodes in the cluster. Some other salient features of CreateDB are that it is ANSI SQL compatible, including joins and Postgres via protocol, which makes integration with tools such as Grafana really easy and prevents lock-in. CreateDB supports distributed SQL with full-text search, JSON, time series data, geospatial data, and blob tables. And this architecture is quite well suited to containerization, meaning that a cluster running on Kubernetes can be scaled up or down in a matter of minutes instead of weeks. And operations like sharding, replication, and rebalancing of data as the cluster size changes are automated. Now, CreateDB has columnar caches for real-time in-memory SQL performance. The real-time databases usually require all the data to fit in the main memory, but that limits how much data you can actually manage. So our solution for real-time performance without data volume limitations was to implement memory-resident columnar field caches on each node. So the caches tell the query engine whether there are records on that node that meet the query criteria and where those records are located. And this all is performed at in-memory speed. Distributed query processing also contributes to fast performance and a query planner that makes very smart decisions about which nodes are best suited to perform different kinds of aggregations and joins. So CreateDB excels at handling the velocity, volume, and diversity of huge industrial time series workloads. For example, industrial sensors often increase the frequency of their measurements when values exceed configured thresholds. Now, CreateDB is able to handle these spikes in data that come with cascading failures without sacrificing query performance, meaning that your reporting and analysis tools just won't stop working when you need them the most. So smart factories have a huge number of sensors for monitoring a large variety of things, such as temperature, pressure, or humidity. And every day, millions and billions of data points are generated by sensors in smart factories, smart cities, and the health industry. And this data needs to be ingested in real time. Since the different sensors are produced by different manufacturers, this data tends to be complex and can be in many different forms. And this data has valuable insights about the operation, which can be obtained from it by performing analytics on the data in real time. So queries like aggregation and time series analysis, along with machine learning or predictive analytical models, are often applied on this data. And the insights that are produced by these analytical operations, they can be used to take action to improve the efficiency and functioning of these various industries, causing significant cost reductions. So the differentiating factor as compared to other time series use cases that should be kept in mind is that these real-time queries are under highly concurrent load. For example, for stream processing and machine learning, and must access gigabytes to hundreds of terabytes of data. So this fire hose of complex data needs to be handled in real time in order to take the actions on the factory floor. So let's now talk about the next layer of the honeycomb built on the core CreateDB technology, CreateDB Cloud, also known as CreateDB on Microsoft Azure. So CreateDB Cloud is a scalable SQL service hosted on Azure and operated 24/7 by the experts at Crate.io. It's quite ideal for industrial time series data processing and other IoT and machine data specific analytic workloads. So it also has real-time query performance for partitioning, parallel processing, and in-memory columnar indexes, which enables real-time complex analytics and AI, not just simple time series aggregates. And it has Azure IoT integration via built-in interfaces to Azure IoT Hub, MQTT, Postgres via protocol, JDBC, REST, and its own native .NET Core driver. So let's now take a look at how you can launch your own CrateDB cluster for playing around with it and testing things, and then we will move on to a case study of a smart factory. So for this purpose, we will be using something called Crowd. So this is a command line tool for managing CrateDB Cloud. So you can install Crowd by using pip. So you can just simply do pip install Crowd, and that will install the command line tool for you. And we have much more information about Crowd available in our documentation. So first of all, we have to log in to our CrateDB Cloud account using Crowd login. So I'm quickly going to do that. So this brings me a window for signing in. So if you do not already have an account, what you can do is you can sign up for free here. So I'm going to log into this particular account and sign in. Perfect. And as you can see, with the command line tool, it says login successful. So once you are logged in, we need to create an organization to which our user would belong. And this organization would also hold our projects. So we can create this using crowd organizations command and give our organization a name. So I'm going to do crowd organizations, and I'm going to create an organization and give it the name August webinar, because why not? So this has successfully created an organization for me, and my user account now belongs to that organization, and I'm the admin for that. And it has given me an output of the ID of the organization. So now under the organization, there can be many different projects. So let's create a project now. You can create a project using crowd projects command, and let's do crowd projects. Now we want to create a project, and we want to give it a name. So I'm going to give it the same name because I'll have just one project under the organization right now. And I have to enter the organization ID under which this project would exist. So I'm going to take the organization ID that I got as output from the previous command and enter that here. Oh, I had a typo. It's not odd ID, but org ID. All right. So here it has successfully created a project for me. And it has also given me the project ID as the output. Now we can finally deploy our cluster with the help of Cloud Clusters command. And so if you think about it, we have a user which belongs to an organization. Organization holds the projects, and a project holds a cluster. So we are going to use Cloud Clusters command, and we are going to deploy our cluster. So first of all, we have to give it a product name. So I'm going to use cratedb.az-gp1. So if you want more information about the different kinds of products that are available, we have a command for that. If you can see here, you can issue crowd projects list and products list, and it can show you the different products that are available and what they mean. So now we have to mention a tier for the product and for the cluster, and I'm going to say extra small here. Then I have to specify a version of CrateDB that I want to put in this cluster. So let's do 3.3.3, and then the unit. So one unit would deploy a 2-node cluster. And then we have to enter the project ID. And we got the project ID as an output from the previous step. So I'm going to quickly copy paste this. Okay. And then, of course, we need to give a name to our cluster. So let's give it the cluster name of webinar class. And after that, we have to, last but not the least, give it a username and password. So let me give it a username of Tane and a password of create hello and some numbers on it. and then I'm gonna issue the deployment command. So it says that the cluster is successfully deployed, and it has also given me different information such as the fully qualified domain name and the URL where you can access the cluster. And since it takes a few minutes for this cluster to actually come online, I prepared one in advance. So let's take a look at what it looks like. So this is the cloud interface. And here you can obtain more information about your organization, your project, and clusters. So this tab currently gives you the overview of the specs of your cluster. And you can see here we are deployed in West Europe region of Azure. And when I put it up, I use kind of the same parameters. So the project is August webinar, cluster's name is webinar cluster. And as said, we have a 3.3.3 version, CrateDB running in it, and a 2-node cluster. Then here we have the metrics tab, which basically shows you different high-level metrics for the cluster, somehow not working right now. And then we have a section for logs. So I don't have any logs right now because this is a fairly new cluster. I have not done anything here. And then we have a section for snapshots of your database and the data present in it, and it's taken automatically every hour. So let's now go to the admin UI and see what that looks like. So here we have the cluster of that we just deployed, and it's the admin UI. And here you can see that's the name of the cluster, version of CrateDB running. You can see it's a 2-node cluster, and we just have a few records, 1,600. Here is a console where you can enter different queries for your data. This is a tables column where you can see the tables that are present in it. What's the specs of the table, like configured amount of shards, how's the health of the cluster. And you also see the schema of the table that is present. So this data, I basically went to the help section here, and you can import some tweets for testing. So it takes the public tweets and imports it into the database in case you have no data to play around with. So I just imported some tweets using that, and let's query the table. So as you can see, we have different kind of objects here. We have time series. We have an object which is in the form of JSON. So let's run a quick query and see what it is like. So I might have mentioned that CrateDB supports full text search. So let's see how it works. So I'm going to select all the tweets, and I want the tweet where text is, let's say somebody mentioned free in their tweet text. And here we get a result. So here we made the use of full text search. So we just have 4 rows here in this case of example. And so we just have 4 people, and we are gonna move on now, as promised, to the case study of ALPLA. So most of the people in the world use their products at least once a week, be it Coca-Cola, Head and Shoulders, or Dove. ALPLA is quite well known in the consumer packaged goods market for its innovative packaging systems, bottles, closures, and injection molded parts. So in 2017 alone, ALPLA produced over 100 billion consumer goods packages. And with over 100,000 tons of recycled plastics, it is also one of the leading packaging companies when it comes to minimizing plastic waste and plastic reuse, also known as the closed loop plastic economy. So we have been working with them over the past 3 years. So this is where real-time information from the production floor has the potential to add value to 180 manufacturing sites in 45 different countries. So they have sensors for temperatures, pressures, blending ratios, and other settings that need to be very precise on every machine. And when these settings are right, high-quality products are the result. And when these settings are off, quality suffers and production costs increase. So imagine a factory floor with 4 production lines, and each of these lines, let's say, have 4 pieces of machinery each. And in the factory, they usually have some sort of visual indicator which shows if everything is working smoothly or not. So in order to discover these issues, multiple people are required to be continuously moving around the factory, checking up on every single machine. So one of the typical scenarios that can happen is that an employee is currently working on fixing the issue on production line 1. And once they finish that, they have to go through all the other lines to check up on the machines. And then that is when they spot an issue on production line 3, machine 4. So upon taking a look at what's up, they realize that some parameters need to be adjusted on the first machine in this production line. And then the person moves again to the first line, to the first machine in this line to fix the underlying issue. So in factories, the production lines are actually laid out over the whole factory, and distances between machines can be quite considerable, meaning that this was quite a slow and labor-intensive operation. Additionally, the latency introduced by having to walk around the factory meant that many products were often affected by a defect before the error was even spotted by an operator. So this resulted in the loss of valuable machine time and a loss of raw material as defective material gets produced till the problems are fixed. So ALPLA's market entry in North America in 2001 was followed by years of tremendous growth. So in 2015, it was already operating 14 manufacturing plants with more than 1,000 employees in the USA. So with this growth came the challenge of hiring and training enough personnel to run the complex manufacturing processes. And because modern manufacturing machines each have a very different sort of complex user interface, every plant required specially trained experts for every machine on every single shift. So as a result of rapid growth, database performance degraded, and response time for queries got longer and longer, and any analytics work on the data was taking more and more time. So real-time actionable guidance on the production floor was no longer possible. So Crate.io built their proof of concept on the top of CrateDB Cloud and enabled them to drive technological transformations. So the first step was to send data to CrateDB alongside the existing SQL database. And the performance of the system improved immediately once this was done. Reports and analytics could be generated in seconds instead of minutes, and the system became capable of giving real-time guidance for workers on the production floor. So this allows ALPLA to establish a closed loop of continuous production state monitoring and process improvement based on the data that is basically read from these machines. So I would now like to share with you the machine data from ALPLA, and then we'll do some queries over this data. So this is the admin UI of the ALPLA cluster. As you can see, they're running 3.3.5 here, and it is a 5-node cluster. And we are holding about 3.1 billion records of data. Now let's take a look at some of the tables and see what the data looks like. And to understand how this works, we shall go along the flow of data. So if you go down and look at the tables themselves, you will notice that we have a lot of raw tables here, or they have the raw prefix. So first of all, raw data comes into CrateDB from the various sensors. And as you can see, we have a couple of tables here containing raw data. And each table denotes raw data coming in from a specific plant. So if you see here, this raw data is coming from the Iowa plant. Here, this data is coming from the Florida plant. This data is coming from the Bethlehem plant. So let's take a look at this raw table. So we have about 37.5 million records here. And as you can see, we have just 4 columns here for the data. And it's timestamp, month, topic, payload, and timestamp. So let's query this table and see what the data looks like. I'll execute this query and I get the different results. So we just have 4 columns here. And let's take a look at the payload for a second. So here we have the payload, which has the topic of bottle underscore counts. And let's take a look at the whole nested object here. So it gives you different kinds of information about the reading itself. So if you take a look at this thing, you can see it gives you a path. And this means that this is a data coming from the Bethlehem plant. And if you remember, we just talked about production lines. So it also tells you this data is coming from production line 1, and then much more information about the specific machines and the machinery parts, and also about the readings. So if you go down, you see we have another topic here called SOPLA measurements. So let's unnest this object. So these objects are basically JSON objects, and they are sending the object in JSON because it works really well with CrateDB. So if you take a look at this payload, you will realize that it is quite different from the payload above. And there are different other topics here which have even different looking payloads. So it is possible to have all of them under the same column because CrateDB supports something called dynamic object. So anyways, once we have this raw table, it undergoes the enrichment process. And during the enrichment process, the data is restructured and optimized for use and query operations. And also the context of various sensors are added to this data to make it much more complete. And since the data gets typed now, it is much more performant on CrateDB. And that is how we end up with the metrics table. So let's take a look at the metric table here. As you can see, we have 1.5 billion records here with 78 configured shards. And if you take a look at the schema now, we have a much higher number of columns here. And these are all strongly typed. So let's query this table and see what the data looks like. So we have strongly typed columns, and all the different nested objects were broken and restructured into different columns here. And if a particular record doesn't have, for example, this particular downtime record or parameter change record, it is replaced with a null value. And the thing about null values in CrateDB is that it does not have any effect on the performance, and it does not take up any space, unlike MySQL. So since we were talking about the smart factory use case, let's do a bit of queries on this data. So I prepared some queries in advance, and I'm going to quickly copy paste them. So here, what I want to do is I want to select the alarm message, alarm unit, and machine model wherever there was an alarm that was created by a particular machinery. But I want the type to be alarm, which is my condition. And also, I just want information on the BMU200 machine, which might be because I might be planning to replace the machine, or because I just maybe want to check the performance of that particular machine and how many alarms it generated. So as you saw, we are iterating over about 3 billion records of data, and we got our query result in about one second. And here we get the different information about the alarm units, like which specific part the alarm came from, and the machine model, of course. Let's do another query, which is also quite smart factory specific. So here I want to find out the line. So line refers to the production line that we talked about. And something important which is worthwhile looking into is downtime of a factory. Because of course, whenever a factory has downtime because of repairs or breakdown or whatever, the factory loses money because things are not being produced. So it is quite important for smart factories to kind of analyze different downtime reasons and their frequency so that they can kind of maximize their gains and make sure that the problems are not happening again and again. So for this reason, I want to see the location of the line, the downtime reason, when the downtime started, when the downtime finished, and how long it lasted, as well as the age of the downtime in hours. And the downtime duration here is being measured in minutes. And I have certain conditions for it. So I want to have the type downtime. And let's say I am a supervisor and I'm going to go to the McDonald's factory. And that's why I'm going to put this condition. I just want the data from the McDonald's factory. And I want to have the downtime reason is cleaning of tool. And I have other conditions like I want it to be ordered by timestamps and a descending fashion. So let's run this query. And as you can see, we have a sub-second query here. And we get the information on the downtime reason, which was we specified we only want to know about the cleaning of tool, when the downtime started, how long downtime lasted in minutes, and how old the downtime was. So this helps me to kind of understand why certain downtimes were much larger than others so that we can work towards knowledge sharing across different factories so that such long downtimes do not happen anymore. Let's do one last query. And I'm gonna copy paste it. Copy pasting is not working very well for me, as you might see today. Well, so this is another query, a rather large one, but it's not that complicated. So I want to know the name of the parameter, the model of the machine, and any occurrences it had in the last 90 days. And I want some of them. And I have a ton of conditions here, such as the machine type should be the molding machine, and different things like it should not include ALPLA measurements and uh, the different parameters that should not include these. So I'm going to execute this query, and again we have a sub-second query or a sub-minute query. We have a query that finishes in 0.4 seconds, and we get the data that we were looking for. And if you go to the cluster tab here, actually, of this cluster to get more information about it, you will notice that we only have 5 commodity hardware running on about 15 gigabytes of RAM and 8 CPU cores. And yet we are able to achieve high performance of queries running over about 3.1 billion records of data with just this. All right. So let's move back to talking about how ALPLA made their technological transformations. So when the Create IoT data platform detects an unusual change in data, like maybe some line has been stopped for a while, or a downtime has lasted a large amount of time, and so this unusual data, it's either detected or predicted, it alerts an expert factory operator in the mission control. And the mission control for ALPLA is based in Atlanta and looks like this with dashboards for different factories from which we got the raw data. So here you can see we have the names of the actual factory here on the top of the monitors to show which data is coming from which factories. Now, when this alert is gotten, the operator alerts somebody at the machine in the factory via a mobile notification system, suggesting an adjustment or repair. Now, since the employee on the production floor has real-time actionable guidance, while they're fixing the first issue, they would get a notification that something is up on production line 3, machine 4, and that they need to make adjustments to the first machine of that line to resolve that issue. So this way, once they are finished with their current machine, they can head over directly to line 3, machine 1, and resolve that issue. So after the issue is resolved, the factory operator logs a note explaining how that issue was resolved. And these notes, as was talked about before, are shared online via online manuals across all the factories to improve knowledge sharing of best practices. And that is how we close the loop, by using this data to take real-time actions on the factory floor. So every plant in ALPLA using CrateDB saw improvements in net equipment efficiency, with some having efficiencies above 90%. And every plant also saw a reduction in manual process adjustments as much as by 50%. So these were net equipment efficiencies, basically is the kind of KPI that they are using to see how well they are running the factory. Now, reducing the number of manual adjustments also stabilizes the processes and significantly improves production efficiency. So the result was a 6-figure saving in 2018. So currently there are about 2.5 million queries per day, and work hasn't even finished yet. It is estimated to increase about 18 times by the end of 2020. You can also take everything that we talked about and move it to the edge. And it is as simple as deploying a few modules on Azure IoT Edge. Because of the sheer volume of the data that is generated by these factories, as you just saw, it is quite possible that at times customers like smart factories would like to store the data on edge for reducing network overhead and latency, so that to take the actions, they do not require such a longer turnaround time. So we recently collaborated on a demo which shows just how to do that. So this sample is hosted on GitHub under our organization and shows how to store machine data from OPC UA servers locally in a single node CrateDB database. So all the necessary components will be deployed by Azure IoT Edge, and we are using these modules for the demo. So first of all, we have a OPC UA server simulation module in case you do not have a OPC UA server, so you can use simulated data. Then a publisher module to publish this data and make it available to different modules on Azure IoT Edge runtime. So this sends data to the edge runtime, which sends it to the IoT cluster running on CrateDB Cloud if you want it to. And at the same time, it is also pushing in data to CrateDB using the CrateDB Saver module, which basically pushes the published data to CrateDB. And then we have an enrichment module that reads data from the raw table and writes it into the metric table, which is not very different from what ALPLA does and we saw. And finally, we have a Grafana module for visualization of this data. So you can use Vagrant to simulate an edge device. And first of all, the OPC UA data comes in, and which is basically machine data. The enrichment module takes this data and enriches in a way quite similar to what we talked about before. Enriched data is then stored in the metric table. And after that, we can visualize this data using the Grafana IoT Edge module. So it's quite easy to connect CrateDB to Grafana because of the Postgres via protocol. Now the time series data can be visualized on a dashboard. And with this, I would like to conclude today's session on the curious case of time series data. So we talked about time series data, the major use cases for time series data, the CrateDB ecosystem for machine data, CrateDB on Azure, and we saw how you can deploy your own cluster to CrateDB Cloud. And by the way, if you are looking for instructions or you didn't get a chance to note them down somewhere, I also have a blog post available on Crate.io's blog post. So you can check it out there. It has illustrations and all the commands that we use. And finally, we did a case study on how ALPLA made technological transformations with CrateDB, along with a sweet six-figure savings in 2018. So we are in this booming age of data. Why not put it to work to make our lives easier, safer, and better? I look forward to seeing what you do with this. And thank you very much.
Thank you, Danai. We've had a few questions come in. Do you want me to read those out to you?
Sure, that would be great.
Okay. So, question 1. In our company, we use InfluxDB. How does CrateDB compare to that?
That's a good question because InfluxDB is quite widely used in the time series world. And as we talked about, there are certain things like certain use cases such as ITN monitoring where InfluxDB might make sense, but in certain cases it might not. So if you talk about like a general comparison over functional similarities, you would say that both of them are quite good at ingesting streams of time series data. Both can partition, query, and aggregate timestamp index data in real time. They both can handle structured and unstructured data, both can do data compression, and both are open source. But unlike InfluxDB, CrateDB includes an SI-SQL standard access interface. So if you are familiar with SQL, you can just use that with CrateDB. And you do not have to kind of learn InfluxQL, which is their proprietary access language, and that makes things easier. And then also to build richer time series application, CrateDB supports geospatial queries, full text search, table joins, subqueries, and user-defined functions as well. For example, for AI use cases, anomaly detection, which saves you both time and work. And if you talk about the kind of performance aspects of it, if you make queries and run them under load, simulating multiple users querying the database at the same time, the performance of InfluxDB begins to degrade. So CrateDB provides better performance when answering queries for bigger user bases or when querying data volumes that span across time partitions. I hope that answers your question. We have a much detailed case study on that. We have a white paper available on our website on the resources section, so you can also check that out.
Great, thank you. I'm conscious of time. Are you all right to take a couple more?
Yeah, sure. Let's do it.
For ALPLA, was the data handling only real-time, or did you manage archival as well?
So we did both. So data is streamed in real time and near real time to enable alerting and all these factory-related functions, right? But we also store all the data in raw, which you just saw. We have the different raw tables, and all that data is stored. And enriched format is also stored in CrateDB as cold storage, so to speak. So archival of data happens in the form of cold storage, and data is also streamed in real time and near real time.
Great, thank you. So I'll just do one more because I'm kind of conscious we're just coming up to the end of the session. Can you share the link of the IoT Edge repository?
Oh, sure. I will send an email after the webinar. I'll reach out to you and I will send an email. But you can also find it in GitHub under our organization. So our organization is great, and you can find that there. It should be named something like Azure IoT Edge demo. So you can find it there, but I'll also send an email.
Great, thank you. So I believe that's all we've got time for today. As I said, we've recorded the session, so we'll send a link to you all within the next couple of days. Any questions that we haven't answered, and I see there's a few more which have come in, we will get back to you over email. And with that, I'd just like to say thank you tonight and wish you all a good day.
Thank you very much, everyone.